Example 6.4, assume steady state at t equal to 0 minus. Determine V1 before and after the switch and I2 before and after the switch. This circuit requires two equations and two unknowns. Now, what makes this challenging here is that this process usually, not all the time, involves a KCL equation that relates I1 and I2 and a KVL equation that relates V1 and V2. And so this is quite different than what we've done in the past. As usual, we are only care about what happens after the switch is thrown at t equal to 0 plus. Okay, here we go. So what I'm going to do now is that I'm going to focus on the initial steady state. And that really tells us about the state at t equal to 0 minus. So here's what you find. So if you look at the circuit is open. So there is no 80 ohm resistor. The inductor goes to a short and the cap goes to an open. So now if I redraw the circuit, here's what happens. So I have a 20 ohm resistor that leads to an open, and I have a source right here, which is 24 volts. And because that second 80 ohm resistor right here doesn't occur, it's this first one that really occurs. And so what I'm going to do here is that now I'm going to come in and I'm going to put my other 80 ohm resistor right in here. So what you're really seeing here is that you're seeing this. I have an inductor current that goes like that. And this inductor current is my first current through this resistor. And according to this resistor, I'm going to have a voltage drop at V01 right here. Now note, this guy right here is the voltage of the cap right here. So what you're seeing here is that immediately you could see that the second 80 ohm resistor is dead since it's in open. So if I come over here, this 80 ohm resistor, which has a current I2 flowing through it, that clearly tells us here that because it's an open, that the current through that 2 ohm resistor must be 0. Therefore, the voltage of that 2 ohm equal resistor has to be 0. So right away, I know what that voltage is. Now, the other thing here is that we have a second 80 ohm resistor, or the first 80 ohm resistor, where V1 of 0 minus is defined is in series with the shorted inductor. Right? So that inductor, which is now short, is in series with it. So what I want to do here is that I want to calculate the values. So now let's go look at that. So if I use Ohm's law, you can see that I have a series circuit. So Ohm's tells me that the current of the inductor is this 24 volt, the 20, and the 80 ohm are in series. So that tells me that I should have 20 plus 80 ohms into 24 volts. This should give me 0.24 amps. And of course, we don't care about 0 minus, we only care about 0 plus. So right away, I know what the current of the inductor is. And this is a thing that can't change instantaneous. So now if I look at the voltage, by the way, if you look over here, we were looking for that current I2. So immediately we see here is that this current is 0. So now the next thing I got to look at is I got to look at that voltage V1. So when you look at that, note that the open is in parallel to the 80 ohm. So now what we're seeing here is that I know that the voltage V1 is also the voltage of the capacitor at 0 minus. But according to Ohm's law, this should be 80 times I1 of 0 minus. But note that the shorted inductor is in series with the 80 ohm resistor. So that means then I know that these two have to have the same one. So this should be 19.2 times 0.24. And that's going to give me, nope, I'm sorry, this should have been 80. And that's going to give me 19.2 volts for the voltage of the capacitor at 0 plus, and it's also the voltage 1 at 0 minus. So now I have my initial conditions here. So now what happens here is that the switch is thrown at t equal to 0 plus. So here's what we know about our circuit. There are two known values, right? We know that VC of 0 plus, that has to be continuous from the switch, and the inductor current at 0 plus must stay the same as well. So what we really got to do here is that because I2 and V1 of 0 plus are resistors, we expect discontinuities. In other words, V1 of 0 minus, I expect it to not be the same as that. And I don't expect the current of this guy this should be 2, not 1, to be the same after the switch. So now what I'm going to do here is that I'm going to apply KCL and KVL like we talked about up here to relate the two currents and the two voltages. So here we go. So now let's go look at the circuit here. So when the switch is thrown, I now have this scenario here. It's customary to come in here and put in back the cap, and we put back in the inductor. But now I have two 80 ohm resistors with this 24-volt source. So what do we know about this? We know that there's a fixed current coming in this direction. That's going to be IL of 0 plus, and we know that that guy is 0.24 amps. I know that there's a voltage across this guy, which we call VC of 0 plus, and that voltage has to be 19.2 volts. So what we're looking for is that we're looking for this current, which we called I2 at 0 plus, and I want this voltage V1 at 0 plus. Of course, this is 80, this is 80, 80, and 20. So what I need to do here is that I need to, in order to solve for these quantities, it's customary to think about this by setting up two equations. So we're going to use a combination of KCL and KVL equations to determine the first one I'm going to calculate is V2 I2 plus and V1 0 plus. That's our goal. So here we go. So now let's do this in steps. So the first step that I'm going to do, I'm going to use KCL to relate I1 of 0 plus and I2 of 0 plus. So I'm not going to write them in, but you can see here is that the current through the second one, to try to make it a little bit clear, if I call the first one 80, I'm going to call this one 80 prime, just to differentiate between these. And the only way I can relate these two currents here is that if I have a node right here, and here's my green node. So I'm going to relate these, and that means here is that I apply KCL at the green node. So if I look at that, the current coming in, right? So the current in has to be the current out. So the current in must be I of 0 plus, IL of 0 plus, plus I2 of 0 plus, plus, oops, nope, equals I1 of 0 plus. Now remember, this guy is for the 80 ohm resistor. Now instead of carrying the 0 plus here, you're going to see that I'm going to drop the 0 plus. But we know that that's the case. So if I do that, look what I have. I then have I1 minus I2 equals to IL of 0 plus. So right away, I'm seeing here that I now know what that current, what those two currents are related to here. Now, The next thing that I'll do here is that what I'm really trying to do is that I now want to use a second set of equations where I'm going to use KVL to relate V1 of 0 plus and V2 of 0 plus. So if you look at this thing, look at the outside loop. So look at how I have. So I have V1, then I'm going to have 24 volts, and then I'm going to have the voltage of the upper one. And you could see here is that this guy is going to have a polarity like this here. So if you look at this guy, I'm going to do this around the outside loop. And if I do it for the outside loop, this really tells me that V1 plus V2 is going to equal to 24 volts. So this is my second equation now. So when I look at this scenario here, note that we are not interested in in the current I1 of 0 plus or the voltage V2 of 0 plus. So what I'm going to do here is that I'm going to convert these variables into what? So if I use Ohm's law, note that they're all resistors. So if I look at the first resistor, that's 80 prime. So note, according to Ohm's law, it should be this. It should be that I1 of 0 plus should be the resistance divided by V1 of 0 plus, and I can convert this voltage V2 as the current through that resistor. So that means I'm going to write this as V2 of 0 plus. This is going to be 80 I2 of 0 plus. So if I convert them, note that I now have two equations. So now what I'm going to do here is that I'm going to get ready to matrix up these equations and get the solution. So here we go. So now look at that first equation. So if I look at that first equation, note that I have I1, but I'm going to convert I1 into V1. So this should be 80 times V1 minus I2, look at equation 1, and that's going to equal IL of 0 plus, which is 0.24. Now look at the second equation. I got V1, but I want to convert V2. So if I'm going to convert V2 using this relationship right here, I'm going to get V1 plus 80 I1, no, it's I2, equals 24. And that's my second equation. So now, if I make a matrix out of this, you could now see that here I got V1. So then this guy should be 1 over 81. I have a second equation, which is going to be an I2. So in this case, this is going to be 80, and this guy's going to be minus 1. And so in this situation, I get V1 I2, and then I'm going to get 0.24 versus 24. And you could see here is that here's my constants right there. So now I have a matrix. So then this tells me that my solution tells me that I'm going to get V1 of 0 plus is going to be 21.6 volts. And then I2 of 0 plus is then going to be 0.03 amps. And that's what I get out of these here. So now let's interpret this. Okay. So I want to interpret mathematically and physically the result. So here we go. So what do I know about V1? So what you're seeing here, that I have V1. So if I look at the voltage here, so let's focus on V1 of 0 minus versus V1 of 0 plus. So if I look at V1 of 0 minus, note that we computed that up here, and note that that was 19.2 volts. So let's look at that. So I'm seeing here that I'm getting that V1 of 0 minus was 19.2 volts versus V1 of 0 plus, I'm getting 21.6 volts. So what you're seeing here is that you're seeing what? These guys are not the same, so there's a discontinuity in the graph. So if I look at this guy, what am I actually seeing here? So if I look at my curve here, so let's draw this out here. So you could see here is that maybe I have a curve like this, and then I have V1 coming in. Okay, I have V1 coming in. Let's say that this is V1. So this is V1 of 0 minus, and this guy is 19.2 volts. And then what happens here is that when the switch is thrown, note that the voltage jumps up to this point right here. And as it jumps up to this point here, this guy is V1 of 0 plus, and that's 21.6 volts. So you're seeing here that as expected with the resistor, you're seeing here that I'm getting what? There's a discontinuity jump in the voltage V1. Okay. Now let's go look at the current here. So now what I'm going to do here is that I'm going to focus on I2 of 0 minus versus I2 of 0 plus. So when I look at this, what you're seeing here is that I2 of 0 minus, well, we didn't have that 80 ohm resistor. So in this case, we then see that I2 of 0 minus was clearly 0. But then if I look at what I2 is afterwards, you could see here is that that's 0.3 amps. So when I look at this, this clearly tells us that we have a discontinuity. Okay, we have a discontinuity. So what does this look like? So if I now look at this thing graphically, here's what we see. I have my curve. Okay, and let's say that this is my curve right here. And this is going to be I2 of t versus T. So I'm going to come in here and note as I come in here, my current at 0 minus is 0. And then what happens? I get a jump here. I get a jump that goes up to this point right here. And that point tells me that this is I2 of 0 plus is 0.03 amps. So what this is telling us here is that there is you could see here is that there is a discontinuity. And again, this should not be a surprise. And the reason why this should not be a surprise here is because the switch radically changes the behavior of resistors in general.